So as Chris said, I'm George Neal. Jim Thompson, my co-author on this work, just waved his hand in the back. This is part of an ongoing series of talks of network performance, which we've been working on over the last year and is being updated constantly. As a matter of fact, I just added a slide 5 minutes ago in grand BSD style. So let's talk a bit about network performance and what we're going to do. And I'm going to try to not move for the video guy. So benchmarks. Benchmarks are hard for a lot of reasons, many of which are listed on the slide. Figuring out what you're going to measure, figuring out how to measure it correctly, verifying your measurement. This is my favorite one on this list, actually, is number 3. Because a lot of people will set up a benchmark, and they'll be like, I'm going to measure whatever, disk performance. I'm going to measure context switch time. I'm going to measure network performance. And then they come up with some sort of reasonable measurement, system, and then they don't verify. They run the thing once or twice, and they're like, it's slow, or it's fast. And for those of us who understand statistics, we know that that's a really big problem. Can our measurement be repeated, right? A lot of people try to measure something that is ephemeral, right? And that doesn't work very well. We're like, well, we know this is a problem. We'll try to measure it, and it doesn't happen often enough or repeatable enough. So there's a difference between repetition and replication, right? So I can say that I have measured, I do a lot of network stuff. So I've measured this networking thing to be particularly at some particular speed, but can someone else replicate that work? And being able to package the things that you're measuring such that other people can replicate your results is called science. And it turns out that that's what we do, or we're supposed to be doing. So it's a really important component of building proper benchmarks, building proper measurements, is can someone else replicate it? If I get hit by a bus between here and Union Station on my way home, can someone replicate my work? This is another good one. This is for any marketing people who have mistakenly wandered into the room, which is your measurement relevant, right? Because lots of people publish a lot of measurements and they're like, this is so much faster on something that nobody cares about, right? So relevance is really important. Is this something that is relevant to the day-to-day operation of the piece of software that you're working on? Or is it a side thing? Or is it something that's only relevant because it's something that you are particularly interested in, right? So engineers, every once in a while, we're like that dog that picks up a bone, and we're like, I'm not gonna let go of it. And you're like, you know what, the VAX, nobody makes a VAX anymore. The way the VAX worked, it didn't matter, or an alpha, or we could list a whole bunch of machines that had particular performance measurements that you could take, or particular bottlenecks that really are not true in the modern world. Computer hardware has changed a lot, and we'll talk about that actually in an upcoming slide. Figuring out how to generate a proper workload, right? So, for those of us who work on networking stuff, sometimes you're at a company where you're like, oh, well, we want the internet to be fast. Well, if we are connected well to the internet, we sort of take the internet and we plug it in. We're like, let's see what happens to the software. And sometimes that works, but that is not a workload that is easy to regenerate, right? So this problem of doing a repeatable measurement or replicating a measurement, that doesn't work because the traffic on the internet changes all the time. 5 years ago, Netflix was not 1/3 of the internet, right? There was something else that was being transmitted, which may or may not have been video. And also, do we wind up with Heisen testing? So Heisenberg, right? Is the cat dead or is the cat alive? Well, if you check, then it's in one of the two states. The measurement itself, does the measurement that we're taking change the underlying performance of the system? And this probe effect is something I'll mention as I go through some of the measurements I'm going to talk about today. Probe effect is really important, and if you deal with people who do a lot of science and benchmarking, the first thing that we'll always say when you present us with a number is, well, what's the probe effect of the thing that you just put on top of the system? And I, not only work in industry, but I do a bit of stuff with, I work with Robert Watson at Cambridge, and we talk to people who are graduate students who are super smart, but not very experienced. And so sometimes they'll come to you and they'll say, I measured this. And you're like, yes, and the tool you used to measure it just slowed it down by 30%. Oh, right. So probe effect, are you affecting the system that you're actually measuring? Network benchmarks tend to be more difficult. Why? Because networks are asynchronous. Programmers hate asynchrony. Network programmers mostly hate asynchrony, but real programmers hate asynchrony because we kind of like things to proceed in order. I do this, 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 and the thing is done. As opposed to I do this, I do this, I do this, what? Right, because that's how networking works. One of the things I like about networking is that we get to call it best effort. So, you know, when Kurt McKusick talks about file systems, he points out that if you curdle someone's data once, they will never trust you again. But networking people, you just keep handing us packets. Like, can you transmit this? Maybe. I dropped it. Could you transmit this again? I dropped it. And you'll just keep giving us packets all day until that thing gets through. It's great, right? So best effort's kind of nice, but it does make doing a reliable benchmark hard because you've got to measure the loss as well as the amount of data that went through. You know, anyone who's got a computer where they're putting data on disk and the data doesn't arrive on disk, they return the disk. Nobody returns the network for that. This internet's no good. I'd like another one. So best effort makes things a little more difficult as well. There is now less of a lack of open source test tools. One of the things I find really amusing in open source, which I've had happen in several different ways over the years, is you'll look around, you'll look on GitHub, which is where software goes to die, and you'll be like, oh, there's nothing there, or SourceForge, which is really where software goes to die. And be like, there's no tools, and you'll start writing a tool, and you'll send a mailing list thing, and you'll be like, all right, so I did this tool, it's not great, and this is, you know, but please use it and tell me what you think. And 5 people come up and they're like, we wrote that tool. And you're like, well, then why didn't you tell anyone, right? You know, like the line from Dr. Strangelove, you know, what's the point of a deterrent if you don't tell anyone? If you keep it a secret, it doesn't work very well. So there are more test tools now. Actually, when I published the one that I talked about here, I got several emails like that saying, oh, we've got something for you. I'm like, great, send me a link. And then the other thing that's really difficult in network benchmarks is control of your system. So generally, when you're running software on a single host, usually you've got relatively good control over the system. Some people don't always do, but it's very hard. It's much harder to control a set of 3 hosts in a forwarding test, or 2 hosts in, you know, a host-to-host test, or a really distributed, you know, large distributed systems test, which is why people often test protocols in simulation. So if you look at things like NS, which is now at NS3, which is a network simulator, this is how most people test things like TCP, because they're like, it's just too hard to set up like a fake internet and have any control over it, so we'll just have this simulated system. So these are 4 reasons why network benchmarks in particular are difficult. So what do you need to do network benchmarking? Well, one of the things you need is a lab setup. So this is part of a network test lab that the foundation, FreeBSD Foundation, has built up at Centex in Canada. We have more machines than this, but this is, when I talk about the things I'm testing today, these are the machines involved. We've got this Arista 10 gig switch. We've got a bunch of Chelsea 10 gig cards, both between the hosts and going over the network so that we can get a baseline. And then we have this thing, which is always called the device under test. All machines at Centex are named after actual animals. That's why we have lynxes and rabbits and orangutans. I thought orangutan was a really bad name. I cannot remember how to spell orangutan. So I was glad when we retired it. But this is a fairly simple 3-host test. If you want to test the forwarding of packets through a system, you've got a source which generates the packets. You've got a device under test which absorbs the packets and tries to forward them to a sink which then measures them. So typical test network. Always important to state this. A lot of people who talk about benchmarks, who don't know what they're talking about, don't tell you what they benchmarked it on, right? Like, what was the chip? What was the thing? You're like, well, we got some 10 gig hardware and some modern servers. Modern as of which week? So here's exactly what we use. So the source and the sinks are dual socket, 10 core each, 2.8 gigs. You can look up on ARC the little names here if you really want to know more about that. Rabbit 3 is a single socket. We got this 7124 is the first real release of an Arista 10 gig switch. 48 or the 50 are the new ones now. And then all the tests were done using the Chelsea T520 dual port 10 gig NICs, which is a PC. What? Yes. Yo. So on the, you probably care mostly on Rabbit. On the source and the sink, they each have All the machines have 32 gigabytes of RAM spread evenly across all of the channels. We were using, well, it matters for the memory speed except for the fact that we're able to generate and transmit faster than, the memory is still faster than the single 10 gig channel, right? Because the PCI bus is 27 or 54 gigs. But yeah, fully populated, yeah, that could be on the page. Fair enough. Point taken, next. So I said we were going to talk about modern hardware. These are some numbers that are relatively important. So at 10 gigs, 14 million 64-byte packets. You have 67 nanoseconds per packet on a 200, or 200 cycles on a 3 gigahertz box to make a decision. Like, do I forward this? Do I drop this? What do I do with it? Turns out cache misses on most modern hardware are about 32 nanoseconds. I mean, each generation of processor is a little different. But so if you have a cache miss, you've blown half of your budget, right, for network forwarding. So this makes things difficult just in and of themselves because you're absorbing a lot of data. But these things then make it all really difficult. So modern multi-core, we used to call these things symmetric multiprocessors. Well, it turns out that a modern Intel box isn't symmetric, right? It really matters where your I/O devices are because they may be closer to whichever processor you're using. One of the reasons that I used a single socket 4-core box here is so that I could avoid the problem of ever worrying about whether or not I was talking to the right socket from memory. I mean, this is cheating, but that's fine. Everyone who asks me what they want to do about high-performance networking, I'm like, you should cheat. Because if you don't cheat, you will lose. So you've got multi-core and you've got SMP. You've got 2 processor boxes. And most modern 2 processor boxes are not symmetric because the link between the 2 processors is not as fast as the link down to the I/O devices. And this is extremely important because if something that is processing your packets is not on the local socket, you are paying a latency and a bandwidth overhead. And when you tell this to people who build chips, they're like, no, it's all right. And you're like, no, it's not. Look at this measurement. No, it's all right. It's a lot of no, it's all right. So this is something that's really important to worry about on modern hardware is multi-core. And then multi-queue refers to all the stuff running on your NIC. So in order to get full performance out of a 10 gig or higher network interface card, all of the NIC vendors have gone to having 1 queue of packets usually per active core on the system. You can have far more than that. You can have less than that. You can tune that. But the thing that will usually come up by default is if you're on an 8-core box and you've got a Chelsea or 10 gig card, then it will have 8 queues, right? And so lining up packets in queues to cores so you don't have cache misses is extremely important. And you can do this on FreeBSD because you can CPU set stuff, which is basically going back to the 1960s. It's like, oh, you will run there, you will run there, and you will, all that scheduling stuff right out the window. So that's why we say lining it all up. In order to get a reasonable benchmark of a system, you actually have to think a lot more deeply now than you used to about what the underlying hardware is, because you've got to make it all line up. And that's because of this cache miss problem. In fact, the thing that costs you the most in networking and forwarding performance right now is not instructions that you're using to do the work. That costs, but the cache misses are what really cost. And this is why I make the joke about the VAX. It's not in this particular presentation, but I presented this before. We still teach people to program as if the underlying computer is, a CPU, some memory, and a bus, and there's a front side bus, and then there's some storage. Like that's how undergraduates still learn. Nobody learns about what happens if you do cache misses, or very few people do unless they're in graduate school. But these are the things for us that we have to care about because that mental model is dead. So I talked a bit about test automation. So this is the thing that I happen to have written, which I may be replacing relatively soon. A system I created called Conductor, simple set of Python libraries written in relatively pure Python. It only requires like one of the install tools. That's about it. But the important part is sort of the mental model here. How do you run a test? Right? So you've got 4 phases. You start up, you set up the system, you load the drivers, because if you've left the driver loaded, then you've got old state in the driver. So one of the nice things about loadable kernel drivers for NICs is on every test, we can bring up the completely reload all of the state so it's blank, add things like ARP entries with ping, and then execute the test. So we've got a startup phase where we get everything set up our routes, and then once all of the players, there's a conductor, and there's players in the audience. Thank you, you're simulating my players. Once all the players get through each stage, they can then go on to the next. So they all go through startup, then they go and they run the test. That's usually starting up something on the source and sink to generate and receive packets. But sometimes it's running on the device under test if I want to collect more data. So we have these tools in FreeBSD, both DTrace and the hardware performance monitoring counter stuff. That's something you can run on the device under test to see where you're actually spending time during one of these tests. Both of those have a probe effect, so you wouldn't want to quote those numbers as like the ultimate numbers you're getting, but it's a good way to use the distributed systems test as a way of collecting data you'll need later. So run phase, then we collect a bunch of data, right? We go out and we get the files and we get the output, and we do a bunch of this stuff. We can automate that, and then this last thing, we reset the system to its original state. Now, if we're going to unload and reload the driver each time, usually the unload is here in the reset. So here's a conductor config. It's very simple. It just tells the software where the subsidiary configuration files are. And then this is a programming language from the 1970s because it's got line numbers. But this was really easy to write because I could use the configuration stuff out of Python to just sort of read this file and execute them in order. But you see here that the player knows where its master is, it knows its IP, it knows who the conductor is, it knows its own, knows the conductor, it's got the ports. I got the IETF to assign 6970 to my protocol, which was hilarious. I did that just to see how long it would take, which is about 3 months. And I applied for 6969, but they wouldn't give it to me. So I got 6970. I tried. I had to be on a phone call to justify why I wanted the protocol number. Well, you see, you've got to be, well, couldn't you do it this way? No, this is how this works. It's weird. It took me like 3 months, but it's fine. And then, so this is sort of the master config, and then here's your phases, right? And there's, these keywords mean things, right? So startup, we bring up the interface. This is an old one. This is Intel NIC. And here's one where we're actually collecting data, right? So I'm like, tell me about instructions retired while executing this test. This is obviously for the device under test. And then we post-process stuff when we're done, and then at the end, well, we just say goodbye. So this is an example config. At the end of the presentation, I've got the links where all of this stuff sits. All of the configs, all of the results, all of the test scripts that I've worked on over the last 9 months are in a GitHub repo, as is Conductor itself. So one of the first things we have to do when we do performance analysis is establish a baseline. And there's a couple of ways to do this. One of the tools that people often use for TCP-based testing is iPerf or iPerf3, which turns out to now be maintained by a former FreeBSD developer, which is nice because that means I can send him patches and he knows who I am. And then the other is we've got a way of doing this using NetMap. I'll talk about both in a moment. So, we wanted to find out what was going on with, 10 gig networking. And we hooked this up. This is the output of iPerf by default runs a 10-second test. And you're like, wow, 10 gigs, sweet. 9.4 gigabits per second. I mean, we're done. I can go home. I can publish this. I'm finished. Wrong. So you'll notice in this that if you actually use pkt-gen instead of TCP, you get wildly different numbers. Because on the source, you've got 14 million packets going out, and on the sink, you do not have 14 million packets coming in. So they've gone somewhere. That thing where we take your packets and we're like, oh, sorry. We did a lot of sorry in this test. So I'll explain how sorry we were. So why the difference between the two tests? Well, anyone who's done enough networking knows that TCP is going to try and use full-size packets. Once TCP ramps up on a LAN, you're using 1,500 byte packets. The systems are doing far less work per packet to forward them. Great. Pkt-gen does what most sort of low-level network testing people do, which is it uses the most abusive packet, which is a minimum size packet of 64 bytes. So with the 64-byte packets, the device under test actually can't keep up, right? because it's getting these 14 million packets per second, which it would not be getting with 1,500 byte packets. All right, let me stop there. So any questions on how we established our baseline? Why we established our baseline? Please tell me you know why we established our baseline. Okay, great. So as I said, we've been doing this presentation for a while now. So each time I do it, I've done a different set of measurements. Yes, sir?
I did actually think of one question.
Yep.
Did you bother to figure out what the smallest size packet you could use?
Yes, so the question is, what is the smallest size packet we could actually effectively forward? And you'll see that after this next section when we talk about how many packets we actually are able to forward and some of the stuff I did to the forwarding, I'm doing to the forwarding code. Right, so each time I present this, I try to present a different set of measurements. Because if I just gave this the same all the time, there's enough people who see me at each conference, you'd all be super bored. Also, the point of this is a longitudinal study through all of the network stack. Like all of the things. Let's turn on all of the things and see how fast or slow they go. So I'm going to talk about two things today. One is we'll talk about IPSec. So in FreeBSD head, IPSec is on by default. If you run default IPSec, default generic, it's on. And one of the things that happened when I did this is someone said, well, have you measured that? And I'm like, well, I measured it when I actually used it. Well, what about idle? Well, we'll talk about that in a bit. Let's talk about what it actually costs to really use. So, why was IPSec not on in generic for the last decade? It's because in FreeBSD, we believe that new features should be hid in a disused lavatory, in a file cabinet, behind a sign that says, beware of the leopard. Right? We don't, for some reason, just turn things on. So I've been reversing that. I turned netmap on last fall, and I turned IPSec on this spring. And of course, people were like, oh, you did? Did you read your commit logs? Anyway, so IPSec and its algorithms. IPSec's encryption is generally computationally expensive. There are offloaded coprocessors. The work that Sam Leffler did years ago to create what we used to call fast IPSec, before the IPSec stacks were integrated, was to be able to take advantage of these coprocessors. Now a lot of that stuff exists on a chip. So there's a stuff called AES-NI, which does acceleration of the AES algorithms directly on your modern Intel chip. Your laptops have it. Modern servers have it, and now we can use it because of someone who's sitting in the room with the green hat. So how do we measure this? So one of the things we did was we do a two-host setup with iPerf 3 using TCP, and then we have Conductor set up the tests, and this is another important point. We talked about statistics. Like just running it once doesn't give you a very useful answer. Running it 10 times might be statistically significant, but it's certainly better than running it once. You can actually determine this. Usually I just ask a mathematician friend of mine, and she says things like, well, what was this thing? And I'm like, that's what that is. She's like, run it no, it should be 12. Okay. Always have a mathematician friend. So this is what we did. We measured it, ran it 10 rounds, 10 seconds each. And of course, one of the first things I did was test the IPSec baseline. So one of the things that did not work when I turned on IPSec was what was called null encryption. And people are like, well, why would you want null encryption? So I could establish a baseline. And this made me so angry, I wrote 1,500 words in Code Vicious about it. So you can go read that later. So we're using null method, no authentication or encryption, no TCP offload on the NIC card. So this is really important. Another thing that most modern NIC cards will do is work really hard to do TCP for you. There's large receiver offload. There's all these features in the card that are like, oh, you don't want to do that TCP stuff. That's hard. I'll do that for you. And that's fine when it works. Not so fine when it doesn't work. But it's a really bad way to do a benchmark because it's getting in the way of finding out what the software is doing. So if we turn off all of that on our NIC cards, we get, these are 2.2 gigabits per second on a 10 gigabit connection. And so we've got the min-max, median, average. So we're getting about, just turning on null IPSec slows us from, nearly 10 gig with all the hardware features turned on to 2 gig, right? That's not good. It gets worse. If you actually ask it to do something, like authenticate the packets without encryption, now we're down to 600 megabits a second. We're less than a gig. But now we've got these instructions, right? So, and by the way, these numbers are not unexpected. It's not like, oh my God, we're terrible, terrible. It's more like, oh, this is expensive, right? And so how do we make it less expensive? So one of the newer algorithms, AES GCM, Galois counter mode. Any French people in the audience, please do not correct my Galois. So this is a test we ran where we compare when we turn on the AES-NI instructions, the device support on the chip in the device driver with what happens when we don't. And you can see when we don't, it's really slow. Like we're now down in the couple hundred megabits per second. And this is with both encryption and authentication. So IPSec actually allows you to have authenticated packets without encryption and then encryption and authentication. And so we turn them both on. In GCM, you're required to use both. That's part of the standard. So, just turning on hardware support without any other tuning gets us from 273 as a minimum, let's see, median, 276 median megabits a second to 1.2 gigabits a second. Now it's not as fast as null, but then we're actually doing something. And this is a good result, but it can be faster. And that's one of the things we're working on right now. So let's take a look at the overall picture. And this is kind of the thing you really want to see when someone's doing any kind of benchmark, but certainly this is what I want to see if someone's going to hand me a network benchmark, which is, tell me what it was when you weren't doing anything real. You're just sort of passing it. This is the cost of the framework. This is the cost of the IPSec framework whenever everyone gets to touch all the packets. And then, here are the actual things that we're trying. So we tried HMAC SHA, and then software and hardware versions of AES GCM. And you can see that we've got min, max, median, average, and then we state the standard deviation because my mathematician friend made me do it. It's also important. So any questions on the IPSec stuff? Right. Okay. Then I will tell the other IPSec story now. So we turn on IPSec in head, which is fine because we've not shipped head yet. Head will eventually be 11.0. And head is where we're supposed to do things like turn things on and make all of the other developers dog food them. So what does that cost? That costs 15% of your overhead for TCP, just to turn that on. But that is a completely naive measurement, right? The measurement is, well, the measurement is not naive, but the implementation has no changes to try and get around any of that. Between now and when 11 comes out, or actually probably between now and the next time this is presented, we will have a better number because we will have actually gone and looked at what it means to turn on IPSec when you're not using it. And then we'll be able to remove all that stuff. Because the other option, which was presented to me in email by a developer who will remain nameless, was, oh my God, you have to turn that off. No. No, you don't go to NASA and say rockets are dangerous, right? You don't come and work on FreeBSD and say, we don't turn stuff on, right? Like, no, we built these things so people would use them. We might turn them off if they actually blow off our foot or, kill astronauts, but only might. Usually what we do is we spend 2 years discovering what was wrong. So currently it costs 15% to turn that on for TCP traffic, and we're going to get that much lower. So let's talk about forwarding. So this is one of the things that has bothered me was pointed out to me, it's been in over a decade. We have a network turbo button, right? So you put FreeBSD on a machine, and then you're like, well, the forwarding's not so great. Why is it slow? And you do a bunch of searches, and then you find web pages that say, well, the first thing you should do is turn on fast forwarding, because we shipped you slow forwarding. What is wrong with us? And so, eventually I get angry enough that I either write something or go and fix the code. So I decided to look into this, and this is the new set of measurements for this particular talk, to figure out what's the difference between forwarding and fast forwarding and what we could do about it, right? Because I don't want to ship an operating system with a turbo button. It's just wrong. Okay, so let's see what happens. Someone asked earlier about what was, where could we actually forward, you asked, where we could forward at line rate. And it turns out in the normal forwarding case where you turn on the vanilla forwarding, there's an IP forwarding sysctl, we can't really do that until you get to full-size packets, right? We don't get 100% line rate until we get to 1500 byte packets. And you can see we can do 7% of line rate at 64 byte packets. That's not so good. That's bad. and it doubles, triples, and then you're like, oh, now we're getting better. But this is the standard forwarding at the moment. So how good is fast forwarding? Well, it turns out fast forwarding is better, but it doesn't make it perfect. It turns out that it's very expensive. And some of the problems down at these small sizes is that the packets themselves are the size of cache lines. And they do things like clog up your NIC and make things really unhappy because you're just constantly putting these small things in that all the hardware has to deal with, both your NIC and your CPU. But you can see that we get to 100% at 1K packets. And even this number, this 54% number, is better than the one before, 41 to 54, 21 to 28. The small size packets are just really hard. And this is the reason people use this as a test, right? People use small packets as a test because they know it's going to be the most torturous test of the system. So we do slightly better on fast forwarding, and you can see we get to line rate sooner. So, well, the first question you ask as an engineer, I hope, is why? Why does this work, right? Are there fewer function calls? Is it just cleaner code? How do we find out the answer to this question? Well, one of the things I did was I used DTrace. So DTrace is something that was put into FreeBSD by John Burrell. It comes from Solaris, and it allows you to instrument a lot of things, including every single function call built during the compile time of the system. So if you happen to know that packets that are forwarded through the system go from ether input to ether output, you can time this. You can also look at where the packet goes by looking at the call graphs. So on your left is the slower function, and on your right is the faster function. Notice that this number is bigger than this number. So here's one answer to the question. There's a lot more steps happening here. You see that there's IP input, IP forward, IP output, whereas in the forwarding case here, there's just one function. It turns out if you execute less code, your system runs faster. That is still true, even if it's not a VAX. So it's true. So we know that we're doing a lot more work to get to IP forward, which is the vanilla forwarding case, than to get to IP fast forward, which is the turbo button. So that's one reason. And if you look into the code, you see how fast forward was implemented. I call this a siding because I'm a train geek. Trains go up sidings and they sit here on a siding, but whatever. IP fast forward was wedged into the system very early on. This is packets coming through the system from left to right. Packets are being received, and then if this was not here, they would go through all of the demux, all of IP input, and then all of IP forward, and the forwarding decision gets made at the end. So if your system is just forwarding packets, you are doing a whole bunch of work here that maybe you wouldn't have to do if you went here. But notice the red arrows. Checking on time. Notice the red arrows. So there's all these escape clauses on IP fast forward, and why is that? That's because IP fast forward can really only handle packets that are nearly perfectly formed. If you ever look at the way packet processing is done in the kernel, you'll see that at every layer, the first part of every function is Goldilocks and the three bears, right? Is this packet's too small, this packet's too big, this packet's just right. But we do that for a lot of things, like are you broadcast, are you multicast, have you seen the devil recently? There's like a whole list of possibilities of things that could be, do you have options, which I think is the one of seeing the devil, in your packet. If any of those are true, then we just shunt it back into IP input and it follows the same old path. There are other problems with this, which I'll mention in a moment, but this is why fast forward is fast. If you have a perfectly formed packet that has no options and nothing strange about it, we will just be able to take it and hand it off. And then I did this time analysis. This is a normal path versus a fast path. This is a aggregation spat out by DTrace, which it does automatically. And the thing to notice here is that in the fast forwarding path, these values are buckets arranged around a number of nanoseconds of latency. So this is a mic. The number of packets forwarded in this big chunk here is far higher than this chunk here. And it's just like, it just takes a lot less time to get from here to here than here to here. So it's time analysis. And this is a little, the reason I point this out here, and I've actually haven't put this into the DTrace toolkit yet in the tree, but I've got a version around in GitHub. This is all of the code that it took to work that out. So I don't know how many lines it is, but it's less than 100. It's less than 50. It's record something in input, record something in output, and then have DTrace do the math for me and tell me what's going on. So when you start approaching these problems now and you're using FreeBSD, you totally want to use DTrace, and you want to steal this script and just do other stuff with it. So there was another question that I had when I started looking at the code. So the way I worked this out was to, measure it and be like, whoa, that's wrong. And then, you just take nscript and you print the code out and you put it side by side. You take a red pen and you're like, oh, these are different. So the first question that popped into my head was, well, it's fine that fast forwarding is fast for that one case. What is its effect on the rest of the system? Is fast forwarding free for everybody else? And the reason you would ask this is you look at the fast forwarding code itself and you look at the beginning of the function and it's doing the Goldilocks thing that happens in IP input as well. Is this packet too big? Is it too small? Does it have options? Does it have all these things? It does the same exact checks that would be done in IP input. Also, if the packet is not going to be forwarded, if the packet is destined for us, then it's actually delaying the host packet processing because it will go through the siding and then at the very end be like, oh, this doesn't need to be forwarded. Put it back into IP input, and then it'll go through IP input, and then it'll get into TCP input, and then eventually, sometime later, your application will get it. So I wanted to measure this. This is possibly Paul Henningkamp's greatest contribution to user space, which is Ministat. And I've used R, and I like R, and I like all these other statistical tools. But you can take 2 columns of numbers and generate a really useful graph with Ministat, which is just a command line tool. So what did I do? I measured the TCP speed between 2 hosts without being forwarded when I just turned fast forwarding on or left it off, right? So the packet would have to go through the fast forwarding code and then be errored out into IP input. And it turns out that we pay a 4% penalty to just turn on, we pay a 4% penalty for TCP to the host just by turning on fast forward. So that means we should take fast forward out, right? We should hide that behind an option that never gets. I'm joking. So that's what we pay. We pay 4%. You can see here, this cluster is, bigger numbers are better. This is the speed of the fast forwarding when fast forwarding's on, and this is when it's off. And then 4% increase, or decrease. Sorry. So what do we really want? Well, first of all, I don't want a turbo button, right? No more turbo buttons. I'm going to get a T-shirt because that's what people do now. We get T-shirts. And what we want is to be able to have the system make a more intelligent choice between fast and slow. And we kind of want a combination of the two. In particular, there are other things that IP fast forward breaks. For instance, it breaks IPSec. Like you can't have IPSec in the kernel and fast forwarding turned on. And that just seems wrong since it turns out IPSec is often used in some forwarding things as well. So it removes this functionality. I believe we can do better. And then when I looked at the code, it's like, well, I could remove the duplicated code. So what we should do is try to forward the packet early and fall back, but remove the duplicated code, right? And so this is what I call try forwarding. And I've got a branch in GitHub that's got this stuff in it, which will eventually, once it's reviewed and tested, or tested and reviewed, I don't know which order, go into the tree. So what do we do? Well, we move the siding around, right? We remove the duplicated code so that if you went back here, probably should have put this in red, this part here and this part here are the same in these two functions. So now, in the new version of fast forward, which I will probably give it a better name, possibly try forward, there are no more Goldilocks checks. There's no more, are you too big, are you too small, are you broadcast, are you multicast, do you have options, et cetera, et cetera. That's all taken care of by IP input as it has been since the beginning of time, right? We depend on the code that's always been here. And now we just have a quick check of, well, if we could forward you, like if you meet like a few really simple criteria, then we'll just do it. But if not, then we'll jump back and, obviously this will not be as fast forward was by itself, but the question is it fast enough and does it reduce the overhead Does it reduce the impact on the rest of the networking stack? That's my goal, is to be as fast as possible and remain general. So these are the similar graph. As you can see, in the try-forward case, we still, this is a different problem. This is something we're going to have to look at to just try and figure out how to get smaller packets to go through faster. But you do see that we get a marked improvement in performance here in the 256, 512, 1K range. And as you'll see on the next slide, so this is old, this is fast, this is the fast forwarding thing, and try. And you can see that other than 1K packets, we're getting really close. Now, I did this on Tuesday, so it's not really optimized yet. But I hope that by the end of next week, I'll be able to find out more of this, and we'll be able to have a unified forwarding path that no longer has a turbo button, that actually has reasonable performance. So I said I added a slide 5 minutes before the presentation. I realized, oh, I should see what the impact of try-forward is. Right? So we know that the impact of fast forwarding on TCP traffic is 4%. So if I go and I muck with, I run the same test because it's all in Conductor, right? I could just run all the tests whenever I want. If I do that, what's the impact? And instead of it being a 4% overhead, now we're down to 1.7%. So I think that's a win. I'm going to put all this stuff up for review. And hopefully by the next time this is presented, I'll have better numbers or more interesting numbers on this. Any questions on try-forwarding? All right, so who's going to commit it for me while I'm standing here talking? Because it's a conference, you're supposed to commit code while I'm speaking. That's what I did. I did that earlier. All right, so I mentioned that this is an ongoing longitudinal study. So we presented work at BSDcon and BSDCan. The two things that were in that are not in this current presentation had to do with the performance of PF between OpenBSD, FreeBSD, and then a similar technology in Linux. We've pulled that out to do new work. If you want to find the old work, it's always going to be online. The slides are always up. And all of the measurements and results are in GitHub, so they're always there to find. Conducted continuously. I'm constantly, coming up with new tests, putting them in, committing them, and pushing them. And I basically, Jim and I proposed this to any BSD conference that's interested to try and present the new results and to get people involved. I mean, part of the reason to give a talk like this is to be like, okay, we're doing this work. We've got a measurement framework for you. We're trying to improve that, and we want people who are doing networking stuff to come and take that. It's open source. Please, steal our code. It's free. Covering more subsystems. I'm going to be diving deeper into IPSec and I'll be doing the forwarding stuff for the next couple weeks and some more IPSec stuff. Looking at driver performance specifically is definitely on my list because different drivers perform differently, it turns out. I know that's surprising. And the next version of this will be given in Stockholm at BSDcon by Jim Thompson. So where can you get this stuff? It's all on GitHub. There are two different repos. The netperf repo is the stuff that's like scripts and tests and config files and results that I've collected. You will have to modify some of these things to suit your needs because the current scripting language isn't very good about variables. So there's a lot of hard-coded stuff. But they're pretty simple. Most of the test scripts are less than a page, even on a non-4K display. Now when you say less than a page, you're like, a page is 100 lines if you've got a nice monitor. And then Conductor itself, the test framework is up in GitHub. There is a port of this, so you can install it as a port package. The measurements themselves have been carried out on FreeBSD and pfSense. The PF stuff that we did a while ago was all done on pfSense by Jim. And then I want to make a plug for this book, which, by the way, this book was written in 1991. It is still the absolute best book on any type of performance analysis you will ever read. It is actually readable because Raj Jain could actually write, which is, trust me, if you've read a statistics book, those people, not very exciting. So the Art of Computer Systems Performance Analysis has an update supposedly September 21st this month. I've told every website that will give me email to tell me when it's ready because I thought he'd never update it. But it's a great book, and if you are interested in this topic and you're interested in the topic of benchmarks and performance analysis, and you want to present performance analysis that isn't just like you going like this, which some people do, you should get this book. So I think yeah, wow, I did it. Questions? Yes, sir.
Have you looked at the impact of the external and both clusters for performance?
So the question is, have I looked specifically at external MBUF clusters, because clusters are always external, on the effect that has on forwarding performance? Actually, I haven't. One of the things I'd like to look at for those people who don't follow all of the networking mailing lists is if I could ever get Roberson to send me Jeff Roberson has an MBUF rewrite that's supposed to make MBUFs faster. But I don't have that code, and no one's ever been able to get the patch out of him. And I figure flying to Seattle with a baseball bat's probably illegal. But we definitely should look at the overhead of MBUFs. The other thing that I'm likely to look at soon, for those people who were at the Dev Summit, Samuel Barrow presented Concurrency Kit. So trying to apply some of those techniques and some of his code to improving some of our hash tables and locking should really help. In particular, one of the things I would like to find out, and we were talking about on Friday, is if we can actually make MBUF tags efficient. So a lot of the subsystems in the kernel use MBUF tags, and they are in linked lists, and those are not very performant. So one of the things there is to look at figuring out the MBUF tag overhead, because a lot of the things like IPSec will use those. Other questions? Yes, sorry. Didn't see you raise your hand.
Just curious, having established a good way of measuring the overhead of IPSec, AES, GCM, did you look at any of the others?
So looked at AES-CBC. AES-CBC and AES-GCM were the only two that we've looked at, and there will be a lot more about that at the EuroBSDcon talk. So we're about to do more of the variants for that. Other questions? All right. Thank you very much. Oh, no, wait.
I'm sorry. So when you were doing your conductor, did you steal any concepts from Grinder, which is a performance tool that I used like 10 years ago? It's written in Python, maybe Python, but it has master slaves, and you can load it, or then there's also load UI.
The answer is no, but I will go look for Grinder.
Yeah, and then look at load UI also from it's part of the Sept UI tool that's used for like network.
Okay. The thing that I'm actually going to look at next, by the way, is the DPDK folks from Intel did something called the DPDK test suite, which is also Python, but has a lot more libraries. And after I get home, we'll be finishing up a port of that so that we've got it in FreeBSD. And they also have master slave and phases and all this stuff. But I'll take a look at Grinder.
Did you have to warm your system up at all? 'Cause I know
Yeah, that's what the pings are for.
Yeah, I know. You
Yep.
have to run things a couple times to get everything all. Yep.
And you run them 10 times, and you then ask your mathematician if 10 was enough. And then she says no. 16 would be better. Yeah, but that's the thing of thinking like warming up ARP caches and things like that.